Okay, recording is started. All right, so good morning, everybody. Welcome back. Hope you guys had a restful weekend after the exam, Super Bowl, everything's good. Before we start today, I'd like to hear back from you guys. How did you guys like the exam? How did it go? Any comments or concerns or just general feelings? Okay, liked it and thought it was fair. Hopefully everyone agrees, but felt the exam was fair as well. Okay, cool. Yeah, hopefully nothing on it should have been surprising. Yeah, catching up can be hard before an exam. Okay, Om Kumar as well. Nice. Okay, let me ask, what did you guys feel like was the hardest component of the exam? Did anything stick out to you as particularly difficult? Yeah, explaining theory is time consuming. Okay. How time consuming would you say? How long did you spend on it? 3 hours. Okay, that's longer than I was intending for it to take. But I suppose if you're doing it open book and you're really searching, making sure everything's correct, it could take you a little bit longer. Mhm. Okay. Marissa, no, all the exams are not graded yet. I should have them all back to you guys by Thursday. My plan is to probably I'm getting slammed with some grad school work today, so I'll probably finish grading them tomorrow. That's my goal. Correct. I haven't posted a new homework for this week yet. So let me cast the screen and I will. No, you don't need to worry about that. But in the future, it's better if you can submit it as a PDF because otherwise I have to spend like, or sometimes I can't convert the file and like it won't let me write notes on your paper. So I want to give you guys feedback. Okay, let me cast my screen and talk about the homework real quick. Okay, cool. We are casting. So there's going to be two homework assignments. Due on not this coming Friday, but the following Friday. So that's February 19th. Okay, so one of those homework assignments is going to have to do with transformations of graphs and like finding inverses and whatever the other thing we did last week was, whatever 1.6 was. What was 1.6? Oh, combinations of functions and compositions and stuff like that. So that'll be one of the homework assignments, and that one will be shorter since we only had like 2 days that week. It'll be a shorter assignment, and then the following homework assignment will be for what we covered this week. Okay, so I don't have one due this Friday, with the exam and everything, I felt like I would give you guys a tiny bit of a break. So I'm just going to append this smaller homework assignment and have it due on February 19th. Okay, so that's how the homework's going to work for the next 2 weeks. So no homework due this Friday, but I'll post the first of the homework assignments today so that you can get working on it early if you want to do it this week. Okay. Any other administrative questions before we start in on the new material? Okay. Well, then let's start. So what are we going to talk about today? We're going to cover section 2.1, which has all to do with quadratic functions. Okay, so we've already been talking about quadratic functions a little bit. Really, we've been talking about quadratic expressions and quadratic equations. And now we're going to talk about quadratic functions, and we're going to talk about graphing quadratic functions. Okay, so it's hopefully pretty familiar to everybody that if we have something and we're calling it quadratic, this is going to have something to do with this ax squared plus bx plus c. Okay, and what we're doing this time is we're going to set that equal to f of x. Okay, so that's going to be the function. So f of x is a function which takes x as an input. So we give it a number and out pops the other side, that number squared and then multiplied by a. And then we take that number and multiply it by b and add that to our previous sum. And then we add the number c. Okay, so that's how a quadratic function works. Okay, and as usual, we require that a, b, and c should be numbers. Specifically, they should be real numbers. And we require a to not be equal to 0. The reason being that if a was equal to 0, then this whole term would go away, and we'd be left with just bx plus c, and that would be a linear function. Okay, so we require that a should not be 0. So this is what a quadratic function looks like. So for an example, you could have like x squared, or x squared plus 3, or x squared plus 5x plus 3, or 7x squared minus 100x plus pi. All sorts of different quadratic functions. Okay, so now let's talk about graphing, right? Because we have a function now, and we've talked about how to graph functions. The way we graph functions is we just take points x, and we take that point x and we plug it into f of x, and the graph of the function will just be all of the points x comma f of x. Where we just take different numbers x and plug them in. Okay, so that's all we're going to do. And the graph of any quadratic function is going to be a parabola. As long as a is not 0, it's going to be a parabola. And we can tell from looking at the sign of a whether our parabola is going to be an upwards facing parabola or a downwards facing parabola. Okay. And the rule we have is that if a is a positive number, okay, if a is a positive number, then we're going to have this opening up, by which I mean we're going to have basically a minimum at one point, and everything's going to go up from there. And if a is less than 0, so that was a greater than 0, opening up. And if we have a less than 0, then we're going to be opening down, by which I mean we're going to have a maximum point here, and everything's going to go down from there. Okay, so if we wanted to graph it, Well, first of all, we already know what the graph of f of x equals x squared looks like because it was in our library of functions, so to speak. So we already should have an idea of what it looks like. But we can always go back to the kind of trusty plug and chug method. So we'll fill in some stuff here, x and f of x. And all we have to do is take some random values of x. I'm going to use -2, -1, 0, 1, and 2. I'm going to use those numbers just because, having some experience with quadratics, I can tell that this quadratic is going to be symmetric about the y-axis. In fact, that was one of our exam questions, was asking whether or not f of x equals x squared was an even function. And the correct answer for that was yes, it is an even function because it is going to be symmetric about the y-axis. In other words, f of x is equal to f of -x. That's what it means for this function to be even. That's just a reminder and a callback to the exam. So that's just to explain why I chose the numbers -2, -1, 0, 1, and 2. I chose all of these numbers so that they would be symmetric about the y-axis. And it's just going to give me 2 points on each side and 1 point on the axis of symmetry. Okay, so let's plug. What would we get? If we do -2 squared, we're going to get 4. If I do -1 squared, I'm going to get 1. If I do 0 squared, I get 0. If I do 1 squared, I get 1. And if I do 2 squared, I get 4. And now all I have to do is plot these points on my graph. Okay, so -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4 are all going to be points on this graph. So let me get some markings here. So we're going to have 0, 0. Let's use light blue. 0, 0, 1, 1, and 2, 4. -1, 1, and -2, 4. Okay. And now I just kind of draw a parabola, which is connecting all of these guys. That's basically all I'm going to do. Okay. And you could take this a little bit further and do like, -3 and 3. Those are going to go to 9 and 9 respectively. And so on and so forth. But if you know the shape of the graph, which we already established that the graph of a quadratic equation will be a parabola, then once you have a few points, you can kind of have an idea of, well, there's only really one way for a parabola to connect these points, right? If we had only just drawn these 2 points here, well, it's possible that our parabola looks like this or looks like this, right? But when we have more points, we can kind of throw out the possibility that it's opening down because there's no way for it to open down and cross through those lower points, right? So the more points we draw, we can kind of pin down how this graph is going to look. Okay. So here's a more complicated one. We've got f of x equals x squared minus 6x plus 5. Okay. And so we can do the same thing here where we just take some random points and plug them in. Let's try using the same points. We'll do, well, why don't we do like -2, 0, and 2. And something like this. -2, 0, and 2. Okay, so -2, we'd get -4 squared plus 12 plus 5. That's no, sorry, this would be -2 squared is positive 4 plus 12 plus 5 is 17 plus 4 is 21, I think. Is that right? And negative 2 squared is 4. Negative 6 times negative 2 is positive 12. That seems really high. That's because this factor says 1 and 5. Okay, yeah, that makes sense. Okay, so we got 21, and then let's try 0, we just get 5. And then if we try 2, we're going to get 4 minus 12 plus 5. That'd be negative 8 plus 5 is negative 3. Four minus 12 plus 5 is negative 3. So let's see what we've got so far. We've got 1, 2, we're way up high. At 0, we are at positive 5. At 2, we are at negative 3. So this is already looking a little bit troublesome. It looks like, maybe we're coming down kind of like this is how we're going to wind up looking. Okay, but this is just to show you guys that this kind of plugging method is only really great if we know sort of where the axis of symmetry is, and then we can just choose a couple points on each side of that and then move on with our lives. But I'll tell you that one really helpful thing for graphing these quadratics is going to be factoring the right-hand side so that we can see where the zeros are. Because the zeros of this quadratic are going to be the roots of the equation, and they're going to manifest in the graph as the x-intercepts. Okay, so try factoring. Well, we've got x squared minus 6x plus 5. We know it should be minus minus, since we've got a minus sign and then a plus sign. So x minus something times x minus something. And we want those two numbers to multiply to 5 and sum to negative 6. So I think we want 1 and 5. So what is this telling us? We can check what values of x give f of x equals x minus 1 times x minus 5 is equal to 0. Well, those are going to be the values x equals 1 and x equals positive 5. So what this is telling us is that we can take these and we can put them into our table here. I'll put 1 and 5, those x values, and we know that those x values produce a value of f of x, which is 0. Okay, and these two kind of key points are going to sort of pin down where our x-intercepts are going to be, okay? So we just go to 1, 0, there it is. And then 3, 4, 5. Here is 5, 0. And those are the roots. Okay, and with our other points, we can kind of fill in what this should look like now. I'll use pink. Should look something like this. Okay. So you could have gotten here eventually by just plugging in lots and lots and lots of points on this table. You would have gotten there eventually, but it would have taken a long time and been a little bit annoying to compute. Okay, so graphing these can be easier if you wind up factoring these things so that you can find out where are the x-intercepts. And by the way, if we want to know what the axis of symmetry is going to be for this, well, it's going to be halfway between our x-intercepts. So the way we would find the halfway point is we'd just do 5 plus 1 divided by 2. Well, that would be 4 divided by 2. That's just 2. I'm sorry, 6 divided by 2 is 3. 3. Okay, so we can tell that this graph is going to be symmetric about this line x equals positive 3. All right. So that's a little bit about how to graph these guys. We can always use the table, but if we factor these expressions, find out where the x-intercepts are, it's going to help us a lot. And what would help us even more is if our quadratic function was already in what we call standard form, which is what we're going to talk about next. But before we move on to talking about standard form, are there any questions about these two examples which I did on how to graph these quadratic functions? Okay. If not, then we'll move on. If you have questions, don't forget I have office hours today after class. Okay, so what is standard form? Standard form is a special way of writing the right-hand side, and this is going to be equivalent to the other way, all right? It's equivalent to this kind of more expanded form, ax squared plus bx plus c. It's just a different way of writing it, because if we were to FOIL this out, this x minus h, and then we'd combine like terms, we'd get something like ax squared plus bx plus c. Okay, but this is what we call standard form. Some people also call it, I think they call it vertex form, maybe, something like that. Okay, and basically we have these three values in standard form. We've got a, h, and k. Okay, so for example, it could be something like 6 times x minus 2 squared plus 3. Okay, something like that. All right, and this a here, we use the letter a here because it corresponds to the letter a in ax squared plus bx plus c, right? Because if we were to FOIL this out, we would get x squared minus 2h plus h squared, right? And then this a would get distributed onto the x squared. So this a is in fact the same a as before. Okay, so it's going to dictate whether we open up or down. And it's going to tell us whether we are stretching or compressing by a factor of a. Okay, so if a is something like 2, we're going to wind up with a parabola which opens up and has a vertical stretch by a factor of 2. Okay, so that's to do with a. So a determines the stretch and compression factor and direction of opening. Okay, and then what is this h here? Well, this h is actually going to be our axis of symmetry. Okay, in other words, it's going to be the x value of our vertex. Okay, it's going to be the x value of our vertex. Okay, so h is going to be the axis of symmetry. And then finally, k is going to be the y value of the vertex. Okay, so it's going to represent our vertical shift, right? And this kind of conforms with our idea of transformations of functions, right? If we were to consider this as a transformation of x squared, then we would know that this k is going to be a vertical shift up k units. In particular, if k is negative, then it would be down. This h here is going to be a shift right h units. So if h is negative, then it would be a shift to the left. And then this a here is going to be our stretch factor. And if it's negative, it's going to talk about reflection, right? And our reflection for a parabola is really just changing the direction of opening. Okay, so this all conforms with what we've already learned about function transformations. And this is just a special way of writing it that makes it really easy to graph these things. Because all we have to do is go to the point h comma k and draw a parabola that opens with direction and stretch factor a. Okay, so here's an example to show you just how easy this is. We want to sketch the graph of -3 times x plus 2 squared plus 12. Then we know that the vertex is going to be at -2 comma 12. Okay, somebody might be like, hold up, why is it -2? Why should it be -2? That's because in the formula for standard form, we have a minus h here, okay? So if we see a plus 2, that reads as minus -2. Okay, so remember, when we're inside the parentheses, we gotta flip stuff and do sort of the opposite of what we think. Okay, so it's gonna be at a vertex of -2 comma 12, and it's gonna open down and stretch factor of 3. Okay, so let's go 1, 2, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's where our vertex is going to be. And we know we're going to open down, and we're going to have a stretch factor of 3, which means that if we have a parabola, right, and we move 1 away from the vertex, typically we go up by a factor of x squared. Well, we would go up by, our function change would be 1 squared. And then if we go over 2, our function change would be 2 squared. If we go over 3, our function change would be 3 squared. So if we're going to multiply that by 3, if we move over 1 unit, then we should go down by 1 squared, and then we should multiply by this 3. So we should go down 3 units. So 1, 2, 3. So this would be the point -1 comma 9. If we go over 2 units, well, ordinarily we would go down by 2 squared, which is 4, but we're going to multiply that by 3 and go down 12 units. So the next point is going to be down here. And I don't really need to worry about graphing things on the left side because I know that this function is going to be symmetric about x equals -2. So I'm just going to copy those 2 points over to the left-hand side. So here's going to be the point -3 comma 9. And then here's the point -4 comma 0, corresponding to 0 comma 0. Okay, and so the whole thing is going to look like this. Okay, parabola opening down with a pretty extreme stretch factor of 3. Okay. So that's how easy it is to sketch these things when we have it in standard form or vertex form or however you want to say it. And so what we're going to learn next is basically if we have something like the graph of the quadratic function which we had before, which was really kind of a pain in our butt, the question is, can we write x squared minus 6x plus 5 in standard form so that it's really easy to see how we should do the graph? Okay, question coming in. Why should the vertex be at -2? Sure, I can explain that again. Okay, so we have this standard form here. So let me get rid of some of my extra stuff here. So the question that Sam had was, why should this vertex be at -2 when inside our parentheses we have a +2? Okay, so how do we reconcile these two facts? Okay, the reason that that's going to be is because in our standard form we had f of x equals a times x minus h squared plus k. That gives us a vertex at h comma k. Now the point here is that if we see a plus sign in our standard form on the inside of these parentheses, is coming from the fact that h is actually a negative number. So if h is -2, then the above would just be a times x minus -2 plus k, and that would be a times x, and when we do minus a negative sign, we get a plus sign. Okay. Okay, so that's why if we see a plus sign inside our parentheses, that's really telling us that h is going to be the negation of that number. Okay. And this is kind of like what we had with the equation of a circle. Right? Remember when we had the equation of a circle, we said x minus h squared plus y minus k squared equals r squared has center h comma k. So in particular, x plus 2 squared, right, plus y plus 3 squared equals 25. That center is going to be at -2 comma -3. Okay, so this is all just coming from the way we write the standard form. Okay, so if we see a plus inside the parentheses, we need to remember that that is going to give us a negative h value. Have I fully answered your question, Sam? Okay, cool. Great question. It is confusing. All right. So let's talk about how we get quadratic equations or quadratic functions into standard form. Okay, so this is all going to be a little bit technical for a second, and then we're going to do some examples which are going to clarify this greatly. Okay, so I'm going to give you the proof in terms of ax squared plus bx plus c. Okay, so we just start with this very general looking quadratic where a, b, and c are numbers. Okay, the first step that we're going to take is we're going to take these two terms, ax squared and bx, okay, and we're going to try to rewrite them in a clever way. Okay, we're going to try to rewrite them in a clever way. So the first thing we do is we factor out a GCF of a from x squared plus b over a times x. Okay, if we were to distribute that a onto those terms in those parentheses, we would get back our original equation. Okay. And now what we're going to do is complete the square inside those parentheses. Okay, complete the square inside those parentheses. So remember, if we have an expression x squared plus b over a times x, we're going to complete the square by getting this number, the number which is attached to the x value. We're going to divide it by 2 and then square it, and then that's what we're going to add out back. Okay, so we take b over a, we divide it by 2. That's how we get b over 2a, and then we square it. And I'm going to add that inside these parentheses so that what's inside these parentheses here is going to become a perfect square. Okay? But remember, if I add something to a function, if I want it to still be the same function, I need to subtract that as well. Okay? So I've done that out here. I've taken b squared over 2, or b over 2a squared. That would be b squared over 4a squared. And remember, it's getting multiplied by this a, which is out front. So in order to undo that addition, I need to subtract by b squared over 4a out back. And now it looks just like how we want, because we can rewrite the inside as x plus b over 2a quantity squared. Okay, x over ba, or x plus b over 2a quantity squared. And then b over 2a is going to be our h. Actually, negative b over 2a is going to be our h. Maybe I should write in the negative sign here. And then whatever's out back is just going to be our k. And then the a, which we factored out right at the beginning, is going to be our stretch factor and direction of opening. Okay, so this is all in very general terms. Okay, and then we're going to get that the vertex is going to be at negative b over 2a, and then the y value of the vertex will just be c plus b squared over 4a. But usually we just write negative b over 2a comma f of negative b over 2a, because as long as we know what the x value of the vertex is, we can just plug it into the function. We already have an expression for the function, and it's not too hard to just plug in the value and get out what the y value should be. Okay, so before we get really confused with this, let me show you an example to show you how this works. Okay, so if we have something like this, x squared minus 4x plus 3, here's what we want to do. The first step is rewrite, where we put x squared minus 4x in parentheses. Okay, now I want to add and subtract the same thing so that I don't change anything, but I want to make this a perfect square. Okay, so I want to take this number, negative 4, divide by 2, and square it. I get negative 2 squared equals positive 4. And that's what I'm going to add. So I then get x squared minus 4x plus 4. But remember, if I add something, I have to subtract it in order to balance things out. So I'm going to subtract that 4 out back. And now this term here is a perfect square. It's a, if we factor it, we're going to get x minus 2 squared. And then the stuff out back will just be minus 1. And then we're done. Okay? So what do? We take this negative 4 here, divide by 2 and square it and add. Okay? Luckily, in this particular example, our a value was just 1, so we didn't really have to worry too much about the a value. Okay? So this whole thing has vertex 2, negative 1. and opens up. No stretch. Okay? Any questions about how we did that one before we move on to the more complicated example? Okay, just so you guys are aware, remember this step is called completing the square. Okay, we complete the square, that's what we're doing here. Okay, let's see this more tricky example. Okay, so for this one, we've got an a value of 5, which is going to make things a little bit trickier. Okay. So first of all, remember the first step was to take these first two terms and take a GCF out of them in terms of not really a GCF actually, but we're going to factor out the largest constant that we can, which in our case is the largest number which goes into 5 and 20, which is just 5. So we're first going to rewrite this as 5 times x squared minus 4x. And then add 8 out back. Okay, so we're just treating with these first two terms for the time being. And now what we want to do is we want to take this guy and complete the square. So I take -4, divide by 2, and square it. Again, I get 4. So here's what I'm going to do. I'm going to get 5 times x squared minus 4x, and I would like to add 4 in here. I would like to add 4 because then this would become a perfect square, and I could factor it as just the same thing as before, actually. X is going to be x minus 2 squared. But I need to balance this out. I've added 4 inside these parentheses here. So I need a corresponding term out back, which is going to undo this addition. Okay, it's going to undo this addition. But if I add 4 in here, remember, it's going to get multiplied by this 5 here. So really what I've done to this equation is not add 4. I've really added 5 times 4, okay? So this is, I'm really adding 5 times 4 equals 20 here. So when I undo that, I have to subtract 20. Okay? Because the 5 would be distributed onto this 4 here if I was going to distribute it out. Okay, so when I add that 4 on the inside of there, I have to be mindful of the fact that everything inside the parentheses is getting multiplied by 5. So when I add 4 inside the parentheses, I'm really adding 20. So I undo that by subtracting 20. And what do I get? In the end, it's just 5 times x minus 2 squared minus 12. So this whole thing has, the vertex is going to be at 2 comma negative 12. Remember, we have a minus sign in here, so we just take whatever that number is, because this is x minus h. So if x minus h is x minus 2, then h should be 2. Okay. So our vertex is going to be at 2 comma negative 12. Opens up with a stretch factor of 5. Okay. So that's how we do this kind of completing the square business when we have an a value which is not 1. Okay, it does complicate things a little bit. So the complicating factor here, the thing which is getting complicated, is this complete the square process. Because when we complete the square on the inside of these parentheses, we have to remember that we're multiplying everything in the parentheses by 5. So when I go to undo the addition which I put in order to complete the square, I have to be careful and make sure that I'm really undoing what I've actually done. Okay. Are there any questions about this more complicated example? Will it always be a vertical stretch? Yes. A is going to represent a vertical stretch. Okay, here's why. If you look at this, if you consider, okay, if g of x is x squared, right? Then 5 times x minus 2 squared minus 12 is g of x with the following transformations. Shifted right 2 units, stretch by, vertical stretch by 5, and then down 12 units. Okay, so the reason that this 5 here, this A, is always going to produce a vertical stretch is because it's lying here on the outside of our parentheses. Okay? Remember when we had a horizontal stretch or a horizontal compression, we would see something being multiplied on the inside of the parentheses with our x. Okay, but we don't see that. Does that answer your question, Savannah? Okay. All right, so let's really quickly talk about, oh man, I did not get through what I was supposed to get through today. Okay, yeah, we'll talk really quickly about domain and range of these functions, and then we'll call it for the day. No. Okay. So remember, the domain of a function is going to be all the possible values which can be plugged in to the function ax squared plus bx plus c, which makes sense. Okay? But remember, the only issues that we ever had with domain were if we were like dividing by something like x plus 1, we had to be worried about dividing by 0, or we had to be worried about doing square roots of negative numbers. Okay? But our function here, ax squared plus bx plus c, it doesn't have any fractions or rational expressions, so we don't need to worry about dividing by 0. And it also doesn't have any square roots or even-powered roots. So we don't have to worry about dividing, or we don't have to worry about doing roots of negative numbers. So the domain of any quadratic function is going to be all real numbers. Sometimes we write this notation. We do an R with an extra line. Okay, so domain of a quadratic function is just all real numbers. And then the range is going to be as follows. If a is a positive number, then it opens up, and the vertex will be a minimum. which means we have h comma k, and we're going up. In other words, the range will be every y value which is bigger than or equal to h. Likewise, if a is less than 0, then the vertex hk is a max, and it would look more like this. And that tells us that the range is going to be every single y value which is beneath h. Okay. So that's how we find the domain and range of quadratic functions. Okay, sorry for going over. That's it for today, and I'll see you tomorrow. If you have questions, feel free to stay after class and ask. I have office hours from now until 10:30. Oh, yeah, you are right, Savannah. Thank you. God, all right. Well, I'll have to correct that next time. That's what I get for rushing, huh? These should be K. Of course they should be K, because K is going to be our Y value. Yeah, thank you. Oh man, I got so low on time. I was like, I just want to get through this. Well, shame on me. All right, well, I'll take a couple minutes at the start of the next class to correct that. Yep, you too. Tommy or Jake, do you guys have any questions about anything?